On to the second lecture for today, generalized linear models. So no required readings for class, but here's some really helpful resources again. I recommend reading more if you are interested. So what are generalized linear models, or GLMs? Generalized linear models calculate nonlinear regressions when you have non-constant variance in the data or when your dependent variables are not normally distributed. So as we mentioned previously, sometimes you know that you have nonlinear or non-normal data and you have an a priori prediction about the need for using a non-standard linear model. For example, you know you could have exponential growth, or if you have binary response data, such as 0, 1s, or you have count data. And so what are the assumptions for these generalized linear models? Well, if you remember back to the linear model assumptions, we had four assumptions. One is that the relationship between the dependent and independent variables were linear. Two, that there is either a multivariate or normal, depending on how many x variables you have, distribution of your error variance, that there's equal variance across your samples, and that there was independence of your observed samples. So generalized linear models take number 1 and 2 a step further and assume that the error variance of the dependent variable comes from a family of distributions known as the exponential family. And the exponential family, which I recommend checking out here on Wikipedia at this link, includes many of the most common distributions, including normal, exponential, beta, binomial, chi-square, gamma, Poisson, Wishart, etc. And many of them work together mathematically quite well. To analyze generalized linear models in R, you use the function GLM with an additional argument for family. And the family argument depends on the type of data you are trying to model, so the distribution of the data you're trying to model. And we're going to talk about 3 pretty common ones here: binomial, Poisson, and inverse Gaussian. Okay, and we'll start with binomial data. So now that we're thinking about how the distributional shape of our data, we need to start thinking about what our distributions look like, if they're continuous or discrete, and what their parameters are. So the parameters are variables that define the shape of the distribution. So here is a figure of 3 binomial distributions with various parameters, and the binomial distribution is discrete. Thus, it's called a probability mass function, not a probability density function, which is what you call a continuous distribution. And so that's why this is represented as points here. Sometimes you can also have this represented as points with a straight line drawn straight down to the x, and that indicates that all of the mass of the distribution, the probability mass, is at that point on the x and y. And so for binomial distributions, which is really just a bunch of Bernoulli distributions lumped together, in case that makes any sense to you. Bernoulli is just a coin flip, 1 or 0. So here, binomials tend to be an observation of 1, which is a success, or for example, survival, or 0 is a failure. So binomial distributions tend to be 0, 1 data. And so we have to dive a little bit more into what these distributions actually look like. And here I've included a link to the Wikipedia page for the distribution, the binomial distribution, and I look at the Wikipedia page for all of these distributions all of the time. There's so much information there, and it's so helpful what the mean and variance of your distributions are, how you define the parameters, etc. I've only included a small piece of it here, so please go check it out on Wikipedia so you can really see all of the information you can find for each of these distributions. But to recap, the binomial distribution is discrete and describes the number of successes in a sequence of n independent experiments or trials. And so you have 2 parameters. It's your n parameter and your p parameter. So your n is in a set of 1, 2, 3, etc., the number of trials, so integer values, and p is the percent of success rate, and that's between 0 and 1. So it's the success probability for each trial. And so this distribution has support for all integer values greater than 0. And the support is important when you're starting to think about where your distribution and your data lie. So if your data lie between 0 and 1, but they're continuous, it could be a certain set of distributions. If it's all values, both negative and positive, it could be normal distribution. If it's all positive values, it could be something else. So once you start thinking about where your data fall, you can start thinking about the support of these distributions and which one might be likely. But the binomial distribution has support across positive integers. And the probability mass function is defined with this equation. If you solve for the right-hand side of the equation, you get the p value that's somewhere between 0 and 1, the probability. And I won't go into too much about what this is, but really it's just the number of trials is your n, and your k is the number of successes, and that's how you solve for your probability of success. And so why would you want to use a binomial distribution if you're doing survival analysis? So 1 equals alive, 0 equals dead. This can be a really useful distribution. I found a paper that showed that someone was looking at mRNA-seq reads, and where you have n reads, or those are considered the trials, with a probability of success p for that a particular transcript or gene was in each read. And so really it's anything with the 0-1 data through space or time. And so let's think about a binomial experiment. Imagine you have seedling survival or days until death due to desiccation of 3 different varieties of soybean. And so you could have a bunch of replicates of these 3 varieties, and you could plot them here. So varieties 1, 2, and 3, pink, green, and blue. And in this data set, 17 days till death means 17 days surviving, so 17 days as 1s, and the rest of the days dead as 0s. And so if you want to actually analyze this data to find out if your survival is a function of the variety of your soybean, to answer the question, does the survival of soybean seedlings depend on its variety? You can use this GLM function, and so your y is a function of your x, the survival, or are you alive or not, is a function of the variety, and you're going to use the family of binomials. And here you can see that, yes, the varieties are really quite different, which is not surprising based on that figure. So another distribution or type of data we could think about is Poisson data. So the Poisson distribution is also discrete, thus it appears as points of probability and that should be at each x, not at each k. And so this is similar to the last binomial graph, except for instead of having points at each x, we now have a point, but a line drawn straight down to the x to indicate where we have the probability mass at each discrete interval. And here we have 3 Poisson distributions drawn here in 3 different colors with different parameter values for k, which is or lambda, which is the rate value. And so the Poisson distribution describes the probability of a given number of events occurring within a fixed interval of time or space. And so here our parameter is lambda, and it's a rate parameter that must be a real number, which is what that r plus means. And it has support across all natural numbers starting from 0. And so it has a probability mass function as well because it's discrete, and here is the function for it. And so what are some biological examples of what Poisson data look like? For example, the number of meteorites greater than 1 meter in diameter that strike the Earth in a year, or the death or births of individuals at a given time, or the number of dispersal events at a given distance. And so let's think about a Poisson experiment. So what would happen if you had Poisson data, and how would you be able to test that? So let's look at the survival of 2 populations of 500 mice, each on a different diet. So one is high in lead and one is high in mercury. And here which are two pretty toxic elements. And here we have time in hours since the diet was fed to the mice and the number of mice from each population that died at each time point. And so if we want to test for is the number of mice that die a function of time, and is there a difference between the two treatments, we would use, again, a GLM model where y variable is the number dead, which is a function of the hours since feeding the food to the mice, plus the treatment, the different diets. And here we're going to use the family Poisson. And here you can see also that time and diet treatments are significant. So this data actually do take the shape of Poisson. I tried it running with just a linear model and it didn't fit quite as well. So when you run it with a Poisson, you can see that the diets are quite different. The pink and blue lines are different, and that time is a good predictor of the number that die based on a Poisson distribution. Okay, and so the final distribution or generalized linear model type we're going to talk about is inverse Gaussian data. This is a personal favorite of mine, so I thought I'd throw it in. But it's really nice because, one, it's continuous, and two, it is described by two parameters, a central tendency mu and a dispersion parameter lambda. And this can be really useful because it's so flexible. When you have two parameters, and they're continuous, these distributions can fit quite a lot of data sets. And so the inverse Gaussian does not have a nice description like the other distributions, but it is a really useful two-parameter skewed distribution. As lambda tends toward infinity, this distribution, the inverse Gaussian distribution, tends to look a lot more like a Gaussian distribution. And so here you have parameters mu and lambda, both have to be greater than 0. There's support for x across 0, all values from 0 to infinity. So again, here's another set of data that if you had negative values, you wouldn't be able to use an inverse Gaussian unless you transformed. But if you have data that fall between 0 and infinity, which is quite a bunch, then inverse Gaussian might be the distribution for you. And this is the PDF, or the probability density function. And again, it's the density here because it's continuous and not discrete. And I'll just make a quick note here that this f of x semicolon mu lambda is saying that this is f as a function of f given the parameters mu and lambda. And so some examples of data you might use here, I couldn't find a whole lot in the literature, but I think it's really a lot more useful than people give it credit for. I know that the dispersal literature uses it quite a bit, so dispersal events over an infinite distance. And so I think that it could be quite useful for a lot of non-negative, positively skewed data. And so what about an experiment? So let's say we have the dispersal of 3 different frog species away from a home pond. Is there a difference in the movement between these 3 species? And so here you can see the movement data is plotted. We have 3 species, X, Y, and Z, and they move, here's their data in these 3 different colors. And so we can ask the question, do species of frogs disperse with different patterns according to an inverse Gaussian distribution? And so again, we run a generalized linear model with distance is the y as a function of species and the family's inverse dot Gaussian. And here we find that species y is moving differently than x, but z is not. And so that's all the examples I have to give you, even though there are quite a few more you could imagine. But please complete quiz 5.2 on Canvas and then continue on to the next lecture.